Good morning, teacher. This is Amy. Today, Mobile and I are going to present our analysis of the summer comfort of the house at number 6 Georges Road. We first studied the 2A and 2B base models, then further carried out a series of iterations on the 2B model. Finally, we reached our ultimate goal, to design a sufficiently comfortable and eco-friendly house that meets the passive house certification criteria.
During the research process, we chose the first 3 days as the research time range in summer and winter design week, leaving circulation space and laundry as the research object of our daytime space, bedroom 1 for nighttime space. The range of 20 to 24 degrees is used for the temperature comfort zone. The first is study of base models. Under the premise that 2A and 2B are all restored to uninsulated lightweight construction and single clear glazing, it is obvious from the chart that the performance of the daytime space is much better than 2A in winter 2B, which is basically in the comfort zone, but it's far worse in summer. The opposite is true in nighttime space, where performance is better in summer and worse in winter. Not only that, but the energy used has also soared from 44,700 kilowatt hours to 81,200 per year, which is in urgent need of improvements.
Our goal for the final result has 2 levels. The first level is more basic, that is, within research time, the mean radiant temperature should not be higher than the mean air temperature by 4 degrees in summer or 2 degrees lower in winter, and reduce the energy as much as possible. The second level is to make our house meet the passive house criteria as much as we can on this basis, which imposed restrictions on the house in terms of temperature, humidity, energy, carbon emissions, airtiness, and other aspects. At present, focusing on the first level, the very obvious problem is that not only the temperature difference is too large, the energy usage has also increased. It is a preliminary inferred that the biggest reason is that our 2B model has added too many and too large skylights, which caused the overall house to be strongly affected by the outside. So the comfortable level is reduced. Therefore, in the first step, we are still ensuring that the daylight factor are still basically higher than 60%. We try to lay out the skylights on the roof. After 6 iterations, we finally determined a more complete state. The annual average energy has been significantly reduced by about 20,000 kilowatt hours, and the difference between the mean radiant temperature and the mean temperature of the daytime zone in summer also narrowed, but the winter of the nighttime zone still need to require to the basic requirements.
The next step is exploration of construction. After trying 3 different best practice construction settings of the design builder system, we find that all 3 tests have met the temperature requirements and performance is similar. In this case, we refer to the Climate Passive House Guide provided by Your Home. Then choose lightweight construction as the base for further iteration. The average annual energy is reduced more than 20,000 kilowatts per hour again. Since our house has a large glazing ratio, glazing design has a great influence on the entire house. After adding shading and changing the single layer glass to double layer glowy glass, the energy consumption is again reduced by 4,000 kilowatts hour per year. After finally adjusting the glass sliding door of the living room to green triple glazing, and the small skylight of the kitchen roof to colorless triple glazing, the energy is again dropped by about 2,000 kilowatt hour per year. At this point, our first level goals has been perfectly achieved. And the subsequent iterative design is the prep for passive house requirements.
After referring to some existing passive house cases, a series of iterative researches on the walls, roofs, floors, and internal walls are carried out in sequences. Throughout this iterative process, we mainly improved the 2 aspects, which are insulation and thermal mass, then adopted environmentally friendly materials as much as possible on the premise of the meeting temperature and energy requirements, and finally present a house that meets the requirement of the passive house. In the end, the model performed well in summer comfort. The difference between the mean radiant temperature and the mean air temperature was about only 1 degree. Moreover, the situation where the radiant temperature is higher than the baseline of 25 degrees is eliminated, which meets the requirement of the passive house. In terms of humidity, the relative humidity is from about 55% to about 45%, and most areas are in the comfortable zone. In terms of energy use, compared to the 2B, the final model has been reduced by approximately 70%, and average annual energy use per square meters has been reduced to less than 60 kilowatt hours, reaching the standard of the passive house. Heating demand has also been lower than the 15 kilowatt hours per year, but cooling is still slightly higher. In terms of air tightness, it cannot be tested because the system is set into 0.75 EC per hour.
The planning drawing reflects the overall layout of the house. The elevation provides a general look and feel. The detail merely shows the cross-section of the bedroom on the west side, the material and the structure from the top to the bottom, and how the incline fixed lowest and side fan provide shading. Finally, our house developed light timber frame structure with composite thermal mat, reverse brick Venice structure for external wall. We use cellulose and environmental friendly installation material on a large area and use hemp block instead of traditional brick. Double layer glass and a small amount of triple layer glass not only provide enough light, but also help in temperature comfort. Compared with timber and aluminum frame, the UPVC frame also reduces a lot of thermal breach and provide better thermal insulation. Since the demand for passive cooling is much higher than the demand for heating, the floor adopts a concrete base without insulation to provide ground coupling.
Our design have taken into account architectural aesthetics as much as possible, based on achieving thermal comfort and environmental protection, and strive to create a good living environment for users.
That's all. Thank you.